Welcome to Advanced Java Programming at Portland State University. In this screencast, we're going to look at some of the fundamental APIs in the Java programming language. We're going to begin with a discussion of the APIs that are part of the Java language. So, the Java programming platform is more than just a language and a bunch of tools like the compiler and the runtime and everything. The platform also has a set of class libraries. These standard libraries provide functionality that ranges from file compression to graphics, a whole bunch of stuff that you don't need to write, and that's probably the powerful thing about it. They also, the standard APIs also embody a lot of good practices for object-oriented programming and can help you learn not so much about Java the language, but in terms of but instead Java the patterns. Although there are a couple of APIs, especially the older APIs, that falls in practices that really didn't pan out over time. And when we see those, we'll call them out and let you know there's some things that you probably shouldn't be doing going forward. Anyway. Here in this discussion, we're going to talk about some of Java's fundamental classes, the useful utility classes, and tools for performing I/O. We're going to spread this out over several screencasts because there's really a lot of information to cover. So, our discussion of the standard libraries will talk about classes in the Java.lang package, the Java I/O package, and the Java util package. But for this first screencast, we're just going to talk about Java.lang. Now, Java.lang contains the classes, interfaces, and exceptions that are fundamental to the Java programming language. We've seen some of these already. Classes like object, right? Everything is an object. The class, which we'll dive into more detail in a later discussion. And the system class, right? You've seen this in system.out.println, for instance, and system.exit. String and string builder. There are a bunch of classes called the wrapper classes, and then exceptions. And we're going to dive more into exceptions, what they are, the different kinds of exceptions, and how you end up with a class hierarchy of exceptions. So, Java.lang object is the root object in Java. Everything is an object. So every class either directly extends object or is a descendant of object. So, therefore, every object in Java, so all of your classes, all the standard API classes, have the following methods. There's an equals method, which will compare an object, this object, to another. The toString method, which returns a string representation of an object. This is often invoked automatically, and we'll see how the overloaded plus operator is implemented shortly. Note that because object is not abstract, it is a concrete class. Each one of these methods has an implementation, but it's a very, abstract implementation. So for instance, toString, what it does, it returns, the toString method inherited from object returns basically the name of the class of the object, the @ sign, and then it's a hash code, I guess. And it's sort of a unique identifier of that object, but it's not very readable. So as you've seen in some of your assignments and as we've discussed before, toString is often overridden to provide a better description of the object on which it's invoked. Every object has a hash code method, which will return, well, a hash code for an object. And we'll see this in a future screencast, how this is really important to the way collections work. And it's fundamental that every object has a hash code. The clone method returns a copy of an object. GetClass returns that object's metaclass, the class. Finalize, we talked a little bit about before, is called when an object is garbage collected. It's not the same as a destructor. Instead, it's sort of a cleanup method. And then there are methods like notify, notify all, and wait that are used in multi-threaded programs. Don't know if we're going to get to the concurrency stuff right away, but in the future I might put together a screencast that talks about how those methods are used in practice. Okay, Java.lang string. We've seen strings before, but now let's dive into some of the details to learn more about it. So strings can be structured from byte arrays, from character arrays, or other strings. And once you have a string object, you can call a whole bunch of methods on it. So for instance, if you want to find the character at a given offset into a string, a given index into a string, use the char at method. String provides a compare to method, which will compare one string to another string lexicographically, essentially alphabetical order. You can determine whether or not a string ends with or starts with a prefix or suffix. Index of will search through the string to find the first occurrence, or actually an occurrence, of a character. Length returns its length. And replace will replace all occurrences with one character with another. And trim will remove leading and trailing white space from a string. Now, actually, before we go on, there's something important that I want to point out about methods like replace and string that change. Replace and trim that they could change to a string, right? Replace will replace characters within a string, and trim trims white space. If you look at the APIs, these methods return a string object, and that's because strings are immutable, meaning they can't be changed. Once you create a string, you can't change it. If you do want to change it, well, you can call a method like trim that will return a different string with the leading and trailing white space removed. If you want to do more complex operations building up a string, there's a class called string builder that has APIs for that. If you're dealing with older code, you might see a class called string buffer, which is used instead. String buffer and string builder essentially do the same thing. They allow you to build up strings out of other data. But string builder is much more performant, and both in terms of operation execution and possibly also memory usage. Anyway, string builder. So I guess if you see old code, you might see string buffer, but if you're writing new code, use string builder. Let's look at some of the APIs, some of the methods that are on string builder. There's the append method, and append will append something to a string builder. And it's overloaded to take all sorts of different kinds of data. As a matter of fact, let's pop over to the API documentation and take a look at it. Okay, so here we are in the API docs, and we want the Java.lang package, and within that we want string builder. There it is. Okay, lots of good explanation on what string builder is all about. And look at all these append methods. And append is overloaded to take, a whole bunch of different values. Everything from primitive types, like booleans and chars and doubles and floats, to character arrays. You can append an object, any object, to a string builder. And you can also append strings and string buffers to string builders. The append method takes an object. What it does is, it goes off and delegates to string.value of an object, which will, when you provide value of a non-null object, it'll invoke toString on that object, and if it's null, it'll simply return the string null. So this is a good example of method overloading. All of these different append methods. So append can be used to append something to a string builder, and you'll notice that the string builder itself is returned by those append methods, and it lets you chain calls to append together. So you can say, let's say you have a variable of type string builder called SB. You can call append, and then call append on the result of that method to keep appending values to the string builder. Okay, there are other methods for mutating string builders. You can delete characters from it. You can insert something into the middle at a given index. You can find the length of it. You can also get a substring of it. Now, usually what you do is you build up your string builder, you append all your data to it, and then you want to get a string representation, because most APIs will take a string, they won't take a string builder. And the way you do that? Well, you call toString, right? This is this toString method that is inherited from the object class, the superclass of string builder. What does it do? Well, it returns, again, a string representation of that string builder. So instead of adding, a new method to the string builder to do this, they just overrode toString. It makes a lot of sense. Now, string builder is used to implement the overloaded plus operator, right? As we saw, plus is overloaded to append some value to a string. And there's really nothing magical about the plus operator. What happens is the Java compiler treats the plus operator as syntactic sugar on operations on a string builder. So for instance, let's say we have this code here. We have a variable temp of type double, and we're going to write to system.out. Today's temp is plus temp. When the compiler looks at it, it's doing the analysis of the source code. It notices that the operands, the arguments to that plus operator, are of type string and of type double. So when the compiler notices that one of the operands is a string, it knows that it's not adding two numbers. It's concatenating something else to a string. So the code that it generates for it is essentially the following. So it's got the double temp, but what it does is it creates a new string builder, appends the string to it, appends the double to it, and then prints out the toString value of that string buffer. So I guess really what I'm telling you about this is that to let you know there's no magic behind the plus operator. It's a little bit of syntactic sugar. And I guess also that when it comes to when you use the plus operator, it creates a new string builder every time, and there is some overhead in that. So if you have an operation that's in a loop that's executed a bunch of times, and this is something that's very performance sensitive, I recommend that you use the string builder API directly instead of using the plus operator. That way you only need to create one string builder, probably outside of your loop, then concatenate all of the data, append all of the data to it inside your loop, and then get your string value, and away you go. Okay, another class in the Java.lang package is Java.lang system. System is a class that sort of represents the VM or the runtime environment itself. And it has some system level fields and methods. So for doing things at a kind of a cross VM scale. It has some static fields. So it has a static field called out. And this is object of type print stream. We'll be learning about print stream later. That represents standard output. So when you say system.out.println, hi, what are you doing? Well, you are invoking the println method of the print stream that is referred to by the static variable out of class system. So the system.out.println really isn't any magic, right? In some languages, printing to standard out is either a built-in operation to the language. I'm thinking old languages like Pascal and stuff, or sort of magic that's sort of hidden for you, like you think cout in C++. You use the left shift operator and everything like that. You need to that seems like magic at first. It's really not when you learn all the details, but there's a lot of details you learn. They have to learn. But in Java, system.out.println, nothing special. There is an object referred to by system.out, and you invoke the println method on it. So just like system.out, there's system.error, which represents standard error, and system.in, which is an input stream for reading standard in. There are also some interesting static methods. Current time millis returns the number of milliseconds since January 1st, 1970. So this is a way of getting, the current time, sort of the system clock. System.exit will shut down the JVM with a given exit code. And we've seen this in some of our in some of the code that we looked at. And it also has some static methods for reassigning the print stream for standard out, standard error, and standard in. You can imagine that that's good for when you want to redirect output to a log file or something like that. Java.math, I won't go into a lot of detail here, but it provides some static methods for performing mathematical calculations on doubles. And so it's pretty much everything that you'd expect. It's a lot like the functions in the standard libraries in C. It's all that same kind of stuff. Okay. So there are some APIs in Java. Unlike the append method on string builder, which is overloaded to take all sorts of different types of arguments, other APIs didn't want to have all that overloading. Instead, they just wanted to deal with objects. So they didn't want to deal with primitives like ints and chars and longs. They just wanted to deal with object types. When we learn about the collections API, we'll see that these guys take objects for things like hash tables or a linked list. However, what if the data that you want to put into one of these collections, what if the data you want to use as a key to a hash table is an int? What Java did to get around this was to provide the so-called wrapper classes that are objects that represent primitive values, primitive types. And so for every primitive type, there is a corresponding wrapper class. So for little b boolean, there's big B boolean. For the primitive type, little b boolean, there is the wrapper class, the wrapper object, big B boolean. Same thing for byte and character, double, float, integer, capital I, integer for int, long, short, and there's even a class that represents void. And we'll see when we talk about reflection why that's necessary. And so these are objects that represent primitive values. And each instant of a wrapper class has methods that can be used to convert between the object and its primitive value. So, for instance, Java.lang integer contains int value. Java.lang character has a method called char value, etc. I want to dive into a little bit of details on this. So Java.lang Boolean has some static methods, and one of which is value of, which parses a string and returns its Boolean value, so true or false. Once you have an instance of Java.lang Boolean, you can invoke methods like Boolean value to return the little b Boolean value for that. And then Java.lang Boolean also overrides the equals method to compare one Boolean to another. I'm sure it overrides string and hash code and things like that too. So character data in Java is 16-bit Unicode characters. So it's not 7-bit ASCII, it's not 8-bit ASCII or Latin, 16-bit Unicode. So characters are bigger in Java, but it's also international character sets, actually intergalactic character sets. There's all sorts of stuff that they have in Unicode. And and you access information about characters in the Java.lang character class. So it has some static methods that will do things like convert between a char and its int value, determine whether or not a character represents a digit or a letter or white space. So, you might think back to your, CS 101 course where you learned about ASCII and you said, oh, well, I know what a letter is. That's easy. It's always in the range, big A to little a. Or actually it's in the range big A to big Z and then little a to little z because those aren't contiguous. Well, in Unicode, there are all sorts of, there's, hundreds of different character sets in there, and who knows what a letter is. And so all of the logic for determining what's a letter or if a character is a letter in Unicode is implemented in this isLetter method because you don't want to do it yourself. Same thing with white space. There are lots of different characters in Unicode for white space. Now, once you have an instance of Java.lang character, you can get the char value, you can compare it to another one lexicographically. I think what's interesting to note here is that they use the compare to method to compare two characters. Okay, so there's a superclass of all of the numeric related wrapper classes, things like int and long and float and everything, called Java.lang number. And Java.lang number has instance methods that's used for converting between all the types. So let's say that you've got a capital B byte, and you want to figure out what its float value is. Well, you could create an instance of capital B byte and then invoke the float value method on it. Since all the subclasses of numbers have similar behavior, we'll just look at one of them. And that's Java.lang integer. So Java.lang integer has some static methods that are interesting. There's parseInt, which converts a string to an int. And I think we've seen some examples of this. We've certainly seen double.parseDouble. And this is how Java chooses to represent this. Thinking back to C, how does C do it? Well, they have a function in the standard libraries called A to I, array to integer. In Java, it's integer.parseInt. You can also convert an int to a binary string, to hex string, to octal string, sort of formatting, stuff like that. Java.lang integer also contains the max value and min value fields, which represent, largest and smallest int, respectively. So you think about how they do this in C, it's done with pound defines. Well, in Java, they wanted to keep the language more simple and sort of stick to existing tools available to them, existing idioms, I guess is a better word for it. And so they said, well, we've got a constant, let's just put it in a static field like max value. Okay, on to exceptions. So we've learned a little bit about exceptions. We saw that there's some things like null pointer exception, etc., etc. Exceptions are objects just like everything else. And what's unique about exceptions? Well, one of the things unique about exceptions is that they all subclass from a class called Java.lang throwable. So all exceptions are a subclass of that. And what does the throwable provide you? Well, it provides you with a method, with a method called getMessage, which returns a string that describes the throwable exception. You can print the stack trace to some destination. And in JDK 1.4, they added something called exception chaining, meaning that one exception can be caused by another exception. And then the stack trace method, when you call get stack trace on an exception that was caused by another exception, you basically get all of the exceptions up the chain. And this was very useful because it helped you pinpoint not only what went wrong, but then also underlying causes of what went wrong. And so all exceptions have those methods. Now, there are two subclasses, there are two standard subclasses of Java.lang throwable. There is a class called Java.lang exception, which is the kinds of things a reasonable program may want to catch. These are things like I/O exceptions, SQL exceptions, and whatnot. And also null pointer exceptions and number format exceptions, things we've seen. Then there's Java.lang error, which is an exception that is truly not expected. Can usually happen at any time and is really quite severe. It's the kind of thing you can't really recover from, like running out of virtual memory or too much recursion on the execution stack. You have a method calling itself too many times, it blows up the stack. These are not recoverable, and you should not try to catch them. Instead, the program crashes. That's the way it is. But because it's an exception, you do, in most cases, get a nice stack trace, and you can get a description of what went wrong to give you an idea then of what you need to do next. There are a whole bunch of exceptions defined in the Java.lang package. Things like arithmetic exception, which you get when you divide by 0. Things like array index out of bounds exception, which is what you get when you try to index beyond the end of an array or give it a negative value or something. Class cast exception, we've seen this one before, right? Where you try to cast an object to a type that it's not. Legal argument exception, null pointer exception, number format exception. These are all exceptions, right? And like I said, there are a couple of error types too, like out of memory error and stack overflow error. So here again, exceptions are things that aren't phenomenally unexpected and something you might want to try to recover from, where errors are truly unexpected, very severe, and really aren't recoverable. Okay, so there is a subclass of Java.lang exception called runtime exception. And runtime exceptions are these so-called unchecked exceptions that are often thrown by the JVM runtime system itself. So for instance, null pointer exception, or array index out of bounds exception. They're unchecked, meaning that they can occur so often that we're not going to bother to force the author of the code to surround it in a try-catch or say that the method in which the exception may occur might throw that exception. Right? Think about a null pointer exception. Every time you access an object, you have to wrap it in a try-catch, or you have to say that method throws null pointer exception. That's ridiculous. So they don't make you catch those kinds of exception. And note that these exceptions are often pretty easy to test for. So for instance, a class cast exception, how do you test for that? Well, you ask whether or not that object is an instance of that. Before you cast, you say, well, is the object really an instance of the class that I expect? And if you do that, you can handle it that way, and then you don't need to worry about class cast exceptions. So the way I think about these unchecked exceptions is that you can look before you leap. It's pretty straightforward. Everything else, though, that subclasses directly from, or indirectly, is a descendant of Java.lang exception, must be explicitly thrown and caught. They're usually called the checked exceptions, meaning that you have to check for them. And examples of these are like Java.io exception, SQL exception, AWT exception. These exceptions are really part of your API. Meaning, think about when you think about your method declarations. What do you say? Well, you say what's the visibility, is it public, what the method returns, int, the name of the method, the inputs that it takes in its parameters, and then what exceptions, what checked exceptions might that method throw. And so this is part of what you're communicating in your API. Now, for this course, when you work with exceptions, I want you to use checked exceptions just to get the experience using them. I feel that in many respects, checked exceptions make your code more explicit and easier to understand because you're documenting, hey, if something goes wrong, here's what might happen, and you're forcing the user of your code to think about those exceptions. That being said, in general, checked exceptions have fallen out of favor with the Java community. And for good reason. They really can clutter up APIs. If you're not careful, you end up with too many checked exceptions. It makes your code hard to deal with. And let's face it, I mean, if something goes wrong, what are most programs going to do with it? Well, just propagate it up the stack and eventually have the VM crash, or have some sort of catch-all, hey, an exception occurred, pops up a dialog box, gives you a cryptic explanation, you click OK, and you keep going. So people have found that in the end, checked exceptions really aren't that useful. But here again, because you're new to the language, because you're learning, I want you to get some experience with them, so you'll be using them in this class a lot. When we learned about the try, catch, finally block, we talked about the fact that when you catch something based on its type. So for instance, let's say that you have an operation like open file, which could throw a couple of exceptions. If the file wasn't found, throw a file not found. Otherwise, if you had problems reading the file or the disk crashed or whatever, you can throw an IO exception. And you want to handle these exceptions differently, right? If the file's not found, we'll just ask the user to enter another file. But if something more severe happened, well, print out an error message, exit the program, do not pass code, do not collect $200. The way that the catch statements work is that they essentially filter out the exception, which means that the order in which the catch exceptions occur is important. So, for instance, if you have the same open file and you go to catch IO exception first, if a file not found exception is thrown, and by the way, a file not found exception is a subclass of IO exception. In this example down here, if file not found exception was thrown by open file, it would get caught by the catch IO exception clause, and no other catch statement would be invoked. If you then, in your source code, said, well, down below here, catch file not found exception, the compiler will issue an error because this catch block down here is unreachable. This is probably not what you had in mind, and this is why the compiler considers it an error, to have a more specific exception type listed after a more general exception type. Okay, assertions. A couple releases into Java, a couple of language versions into Java, they added an assertion facility. I don't know if you guys are familiar with assertions from C or not, but the whole idea is that as you're programming, I don't know about you, but when I program, I have a little story going in my mind. And the story is sort of understanding, hey, what do I expect to be going on here in the program? And so, and a lot of the things that I'm saying to myself are based on, well, for lack of a better term, assumptions that I'm making about my program. Okay, well, for instance, this variable should have a non-negative value. Oh, this object reference should never be null. And I make all these assumptions as I'm writing my code. Now, what an assertion statement allows me to do, an assert statement, validates my assumptions at runtime. I'm basically asserting that, oh, I expect this value is not null, or okay, I expect that after I perform this operation, the size of the buffer is 0. Something like that. And so I can use this assert keyword in the language to basically assert assert whether or not some expression is true or false. And if this expression here evaluates to false, then an assertion error is thrown. Remember, an error is something very severe. You're not supposed to catch these things You're not, and because you really can't recover from it. Uh, in this case, you're basically that logic that you had built your program on, those assumptions that you had made, turned out to be false, turned out to be wrong. That's a pretty severe thing, right? It basically means that your code is wrong, or that there's some state that your code is not handling. So your objects have gotten in, or your code has gotten into a bad state. So you can make these assertions. Oh, and by the way, there's a variant of the assertion keyword that takes another expression, which is a detailed error message that is issued with the assertion error. You'll see some examples of it in a minute. So note that assertions incur some runtime expense. You have to evaluate expression one. You have to make sure you have to check every time an assertion is evaluated, whether or not that's true or false, and there's some runtime expense in that. So by default, assertions are turned off in Java, are disabled, meaning that you can compile the assertion and still learn the bytecode, but unless you explicitly enable it, the assertions won't get evaluated. And the way that you enable the assertions is with a -EA flag to the Java virtual machine. EA, of course, stands for Enable Assertions. Also important to note that the code that is executed as part of the assertion, either expression 1 or expression 2, must not have any side effects, meaning that it shouldn't change the state of an object because it's not always invoked. So it's not always invoked because assertions aren't always enabled. So you just need to be extra careful when thinking about your assertions. Now, normally your assertions are just very, very simple. It's like hey, I assert that O doesn't equal null, or I, assert that value is greater than 5, things like that. So what I would recommend is that as you're developing your code, you initially run your unit tests, and when you run it from the command line, run it with -EA, with assertions enabled. And then once you've proven to yourself that your code works as expected, and so that all of if all the assertions pass, it means that, that means it's very likely that the assumptions that you made were correct. Once you have validated all of that by doing some testing with assertions enabled, turn off assertions, do a smoke test of your code. It should run a little faster, and then move on and then submit. So we've seen two mechanisms, two facilities for alerting the caller, alerting the user to something that has gone wrong. We've seen assertions and we've seen throwing exceptions. So when should you use each? Well, I say use assertions when you want to verify the internal logic of a method. So this is inside a method, you've built up some state, you've made some assumptions, codify those in assertions. But this is only the internal logic of a method. If you've got a public method, for instance, that let's say needs to do some input validation, don't use an assertion for that. Instead, because it's public, right? And so the assertions may or may not be invoked. Because it's public, use an exception, something like legal argument exception or null pointer exception. So, hey, you've got a public method, someone takes a string, you're sent a null string, what should you do? Well, throw a null pointer exception. Because remember, it's reasonable for a program to catch an exception, even a null pointer exception. Somewhere out there, up the call stack, it can catch a null pointer exception. But your programs really shouldn't be catching errors. They can, but they shouldn't. And when an assertion fails, it throws an assertion error. So here's an example of when to use assertions and when to use exceptions. Let's say I've got a public method on my API called setPort. It takes in int. Now it doesn't allow ports that are less than or equal to 1024. So here I want to validate that the port argument that's passed to me is valid. And since it's a public method, what do? I say, well, if the port is less than or equal to 1024, then throw a legal argument exception. Contrast this with a private method that reads the port from a configuration file. So what does it do? Okay, well, it does whatever it has to do to read it from the config file. Before it returns it, it validates that it's a valid port by asserting that the port is greater than 1024. And by the way, if it's not, it'll issue a message with the value of port in it. This is an assertion because it's a private method, and because we're making an assumption that that by the time we've actually read the contents of the file and found the port in it, that this is code that's all under our control. The configuration file, or maybe a database is a better example. Here again, all sort of under the control of the program. So we're going to make a very strong statement. We're going to assume, we assert that the value is greater than 1024. Assertions can also be used to verify program logic. So let's say you're doing a switch statement on a day, and you cover every day of the week. If you get down to the default, it means that you've missed a day of the week, and that's a pretty severe thing. So I'm just going to say assert false. Say, whoa, if I get here, I've got an unknown day. I don't even know what the heck that is. So that's a pretty severe thing. And because what it means is that this code is a fundamental misunderstanding about the day, the various values of day. Another example is doing the mod operation. So let's say, okay, if imod 3 is 0, go do something else. If imod 3 is 1, go do something else. Otherwise, whoa, imod 3 better be 2. Otherwise, I don't understand what mod means. Assert that. Okay, great. If that passes, my assumptions were correct. I'll go about my merry way. The bottom line is that using assertions will make your code better. Because essentially what you're doing is you're adding internal validation logic to your code. Now, of course, you can go overboard with assertions. You don't want to assert everything. You don't want every other line in your code to be an assert. But using assertions judiciously will help you find defects in your code and will then give you more confidence that your code does the right thing. That being said, there's a counter argument to using assertions, which is that, well, you should have unit tests that cover all of that logic, and you should find during development the improper assertions that you've made about your code, and so then by the time all your unit tests pass, you shouldn't need assertion statements in your code. I can understand that argument, but the nice thing about assertions and by leaving them in your code is that when you get beyond unit testing, let's say you get to scalability testing, or you've deployed in production, or you're about to do a pre-deploy and you're doing lots of testing, those assertions in your programs can still get executed, and it's good to make your assertions against real-world live data in addition to the kinds of things that your unit tests put your code through. Okay, I want to touch a little bit more on the clone method inherited from Java.lang object. A clone makes a copy of an object, and the copy usually has the same state. So we say that, hey, we have some object and we clone it. Well, we get an object back which is equals to the original object. Now, a clone creates a different object, so the clone of an object X is not the same as the object itself. Now, the clone API is a little weird. I think in hindsight, they did it wrong. I think pretty much everybody admits that the clone API isn't the right thing to do. So I'm just going to touch on it briefly here because it's something that you might encounter. So every object has a clone method, but it's protected. And the way that you make it public is by implementing a interface called clonable, which has a public clone method. So now when you implement clonable, you get a public clone method. And there is some magic inside the VM that will sort of automagically return what's called a shallow copy of the receiving object. The VM is smart enough to know that, okay, when clone is invoked on a clonable object, it basically takes the original object, makes an in-memory copy of it, and goes along its way. This is kind of interesting. No constructor is invoked. They basically make a structural copy of it, and it also means that the fields of the cloned object have the same values as the receiver object, the one that was originally from which it was cloned. And this is why it's called a shallow copy. It only goes so deep. If you want a deep copy, you need to override clone and implement it yourself. So let's say I have a class called grades that has an array of doubles. It implements clonable, and I want to have a deep clone of this class, of this object. And so what I do is I call super.clone, which sort of makes a shallow copy, and then I copy the fields that I want to be copied in the deep copy. So I basically clone the grades field, and I return that one. Note that arrays are clonable because they are objects. And another one of the wonky things is that even though clone doesn't declare that it throws clone not support exception, it still needs to be caught. So I don't know if we'll be seeing cloning in class. Actually, probably won't. But if you ever encounter it with real Java code, well, that's what it's all about. Okay, the last thing I want to talk about in the language API is something called covariant returns. Now, this is kind of an advanced feature of the type system. It's actually easy to understand, but it's got this fancy name, covariant returns. The whole idea is that if you have a method that overrides another method, the overriding method may modify the return type of the method it overrides to be a subclass of the overridden method's return type. And here I have some example code here. So for instance, and this is relevant because it comes in really handy with clonable. So if you look at the signature for the clone method, it returns an object. And this means that when you clone an object, let's say you clone a string, well, because the return type of clone is object, you then need to cast the return value of the clone method to string, and then you can use it as a string. Well, what covariant returns allow you to do is the following. So let's say, okay, I've got an animal implements clonable, and its clone method returns object. Well, I can subclass animal into human. I can implement a clone method on human, and because of covariant returns, the return type of the clone method can be human, not object. And the compiler is totally cool with this. What this allows me to do is to say, hey, return new human. And then if I have an instance of human and I clone it, I don't need to cast anymore. Similarly, I can go down the class hierarchy, and my clone method of student can be typed to return student. So this makes things easier because you don't need to do as much casting, and also makes it much more explicit what's happening with a method like clone. Now, I was curious about how covariant returns were implemented, so I decompiled the class, and I found some kind of interesting things. The class file for a human still declares that the clone method returns an object, and this gives you binary compatibility with older code, meaning that you can mix and match. However, when you call human.clone, the return type of the actual invocation is human. So this is kind of interesting. Anyway, just one little last note on covariant returns. It's possible that before if you have an old API that didn't use covariant returns, and you then make a modification to it so that it does use covariant returns, users of the old API might be affected. So for instance, let's say you had some old code that extended your human class to have a professor class, and it overrode clone. And it's not using covariant returns, so it is it returns its return type of the clone method is object, which is all fine and dandy, except if you then go to recompile this with the new human class whose clone method overrides clone to return human, this professor code will no longer compile because the clone method that now overrides the clone method that returns human returns object, and you can't, when you override with the covariant return, you can't make the return type more general. You can only make it more specific. So you can't go that way. Right? This code wouldn't compile because object is not a subclass of human, it's the other way around. One other place where covariant returns come in handy is when you have external APIs and internal APIs. This is a common pattern. The whole idea is that, hey, to the world, you expose one interface, but then internally, you have an implementation of that interface that's internal and probably adds some behavior that's only needed internally. So for instance, let's say that I've got an application that models a classroom, and in that classroom resides in a university. So I've got university, I've got classrooms, and get classrooms and things like that. Those are all interfaces, right? What we want to expose are very abstract things like interfaces. The internal APIs will contain the implementation of those interfaces, the classes that implement those interfaces. And so you have a classroom impl, and then you'd have a university impl. Well, because of covariant returns, your get classrooms method of university impl can return classrooms impl. And this actually comes in really handy. So your internal code, it only has to deal with the internal APIs. And so this means that you don't have to cast as much, and so that you can be more explicit about what's available. Where your external code, it can just be happy programming to the interface, uses all the abstract stuff. It doesn't care about the implementation classes. It can just use the externally facing one. Okay, well, I think I've talked for long enough tonight, and so I want to stop here. We'll continue our discussion, though, in later screencasts, exploring more of the standard Java API. So thank you for watching the screencast for Advanced Java Programming at Portland State University.